Good morning, everyone. In the previous lecture, we finished the topic of kinematics of rigid bodies. And just to remind of the main results there, we derived a set of equations of motions known as the Euler equations for rotational or rotating systems. And we applied these equations to a couple of examples. For instance, the gyroscope effect we had a pretty detailed look at. And we also considered how a symmetrical top would precess and move under the influence of solely gravity. So today we'll change the topic and we'll have a look at something known as small-scale oscillations. And this is a topic which is highly versatile. It has applications in many areas of physics. So let me just list a couple of these areas so you can see where you might find use for this type of theory. So two of these applications are vibrations in molecules and also lattice vibrations in solid-state materials. And these type of lattice vibrations can actually be fundamentally important for determining the physical properties of solid-state materials. So these play a very important role here. So two more applications are vibrations in mechanical systems. You can imagine that you have, for instance, a set of harmonic oscillators somehow, which may or may not be coupled, like springs attached to each other. In that case, you would have a mechanical system with vibrations. And also, in fact, this theory can be used to describe oscillations in electrical circuits. For instance, by the application of some AC component, you can get oscillating currents or voltages, for instance. So we find application of this theory in several sub-areas of physics. Now, before we start by deriving a quite comprehensive formalism, which also you'll find is very general, we'll just recap briefly what we know about the simplest case of a 1D harmonic oscillator. And I won't spend a lot of time on this, but this is just to get you in the correct mindset. So the harmonic oscillator typically has this form. The potential looks something like this. And we may speak of the curvature of this potential being defined as the second derivative of the potential, which becomes k. The equation of motion looks like this from Newton's second law. And we see that in general, the solution for the position coordinate can be written in quite compact form. like this. And here A is a complex coefficient, and omega is some real frequency. So it's important here that A is complex. Because if A is a real constant, then this becomes A cosine omega t. But is this the general solution to this equation? Yes? Well, in fact, you can also have a sine solution. So the general solution to this equation is a superposition of cosine and sine terms. So if A is a real constant, we only get the cosine. But if it's a complex constant, we get both the cosine and the sine by multiplying these two with each other. And also, let me attach a zero there. This so-called eigenfrequency is given by the mass and the spring constant or curvature like this. And as we know, the result here then is a harmonic oscillation with frequency omega 0. We can extend this very simple model to include friction if we like, and we do this by incorporating a term in the equation of motion which is proportional to velocity, or x differentiated with respect to time. And so we include this force, which net effect is to introduce a damping in the system. So we get this additional term in the exponent here. Like this. So you see we get a damping. Or possibly if lambda is negative, we actually get an exponential increase in the oscillation. So all of this stuff is hopefully well known to you, and it serves as the foundation of what we'll do next. So we'll begin by just making a few assumptions about our system, which are quite general. So we assume, as pretty much usual, that we have a conservative system and that the constraints here are time independent. So if we have a system with large m particles and k constraints, we know that in 3 dimensions in general we would have 3n minus k degrees of freedom. So assume then that we have taken the position vectors of each of these n particles and transform them into a set of generalized coordinates which are independent, where the constraints already have been taken into account. So this type of procedure corresponds to what we did in chapter 1. Okay, so let's now try to say something about the equilibrium state of the system. If someone came up to you and said, okay, so you're a physicist, how would you describe or put into words the condition for a system to be in equilibrium? If you have a system of large n particles, what would you say corresponds to the equilibrium state of the system? Mm-hmm.
There is no energy exchange occurring within the system.
Mm-hmm. I'm trying to think of, trying to see if that is fully correct. Yeah, I think you can formulate it like that. Did you have a comment also?
The net force on the particle is zero.
Yeah, that was originally what I had in mind. So you can say that the net force exerted on particle I, on each particle, is zero. So that also that should correspond to the case where there's no energy exchange between the particles. Right. So for this type of context. So we have the following mathematical condition. The generalized force acting on each particle I, which is provided like this, the partial derivative of the potential with respect to the generalized coordinate qi, should be equal to 0 in the equilibrium state. And this 0 here indicates that we have to evaluate this derivative at the generalized coordinate value, which is this equilibrium state. You see how I mean? Okay. So basically, so this condition means that we have an extremal value of the potential energy in the equilibrium state. So the equilibrium state is provided by Q01, Q02, etc. So these are positions or values of the generalized coordinates which give the equilibrium state. So using this mathematical condition, we can envision at least two possible scenarios. So we can envision the potential energy plotted as a function of Qi. So we basically project the potential down to a particular axis, say Qi. So then we know that in the equilibrium state, denoted by Q0i, the potential should have an extremal value. So it's either a minimum or it's a maximum. And the value of the potential at this configuration we can denote E0. So these two types of equilibrium are qualitatively different. This is a stable equilibrium, and this is an unstable. And to understand this, consider the following. The system will always try to minimize its energy to reach the ground state, or the lowest energy configuration. If we now are positioned in this equilibrium configuration and we perturb the system slightly, so we change the value of Qi from this equilibrium value to some slightly perturbed value, we see that the energy increases, the potential energy goes up, which means we're no longer in the ground state. On the other hand, if we do the same thing here, we see that the energy is lowered, right? So this means that we have an unstable equilibrium. You can use an analogy here of, say, a ball rolling down or up a hill. So if you have a ball here and you kick the ball, it's going to roll up a little bit and then roll back down. This is a stable equilibrium position. Do the same thing here, it's going to keep rolling. That's an unstable equilibrium position. It's still an equilibrium position, but it's unstable to perturbations. For an unstable equilibrium, a perturbation from this equilibrium configuration gives an unbound motion. Now, the title of this topic or chapter was small-scale oscillations. So what we'll do to begin with is just consider how the system responds to a small perturbation in the generalized coordinates. So we write the generalized coordinate as an expansion around its equilibrium configuration. So the perturbation here is denoted eta I. Now Qi is our generalized coordinate. Q0i is just a constant corresponding to the equilibrium configuration. So we might just as well consider eta I, the perturbation, as our new generalized coordinates. It's just a linear shift compared to qi. So to get an idea of how the system will behave as we perturb it, we'll perform a Taylor expansion of the potential energy in this parameter. So we're going to expand this potential around the equilibrium point, which gives us to lowest order, of course, just its value at the equilibrium point. The next order correction to this result is the derivative of the potential in the equilibrium point multiplied with this perturbation. We can take one more. So this will be the second order correction, just the second partial derivative. So note that we've used the sum convention here. We have repeated indices, implying that we have a double sum over I and j there. Okay, so are we any wiser due to this? Well, there are at least two things we can do here. First of all, we know the value of this. It's 0, because the potential has an extremal value in the equilibrium configuration. Is there anything else we can do?
The first term is just a reference level, so we can set that also to 0.
Yeah. This is just some constant which has no implication for the physics, so we discard it. So we end up with this. And let me define this. In the following way. So this Vij quantity is now to be understood as the partial derivative of V with respect to the generalized coordinates Qi and Qj. So what this equation tells us is that the potential energy at the value of a generalized coordinate slightly perturbed from the equilibrium configuration is given like this, where eta I and eta j are the perturbations. And as long as V is a well-behaved mathematical function, we also have that it's symmetric. We can just exchange the order of derivation. Okay, so that was the potential energy. Let's now have a look at what happens for the kinetic energy. And the motivation for this, as you might suspect, is that once we have the kinetic and the potential energy, we can write down the Lagrangian of the system, and hence obtain the equations of motion. So what we'll do here is that we'll generalize the ordinary expression for the kinetic energy, which is 1/2 mass velocity squared, to this double sum. So we consider a matrix, if you will, M with elements Mij. And so we take into account the fact that we might have cross terms in the velocity. So if you just consider a free particle moving, then you would just have a diagonal matrix, right? You would only have non-zero values for equal coordinates, so you get 1/2 mx dot squared plus y dot squared, for instance. So we consider the possibility that we might have cross terms here to make it more general. And so if I insert now my ansatz for this generalized coordinate, we get this. And to make the situation even more general, we consider the possibility that these mass coefficients can actually depend on the generalized coordinates. Like this. So we perform a similar expansion of the mass terms as for the potential. So again, for the simple case of a free particle that we may be accustomed to, only this constant term would contribute. And it might seem a bit weird to have these mass coefficients actually depend on the coordinates in the system. But in fact, this may be more familiar to you than you suspect. So let's see. Consider 2D motion and with the description using polar coordinates as our generalized coordinates. For which case the kinetic energy looks like this. So we see immediately that this mass coefficient here depends on the radius. So the matrix coefficients would be the following. Now we have a potential energy that is, we have written up to second order in these sort of perturbations from equilibrium. So we should keep the same order terms in the kinetic energy as well. Oh, sorry, did I point here? Here, the potential energy is second order in these quantities. Now the kinetic energy is already second order in these. So we only have to include this lowest order term in the mass in order to get a second order expression in the kinetic energy. So it means that we can write the kinetic energy in the following way, completely analogously to the potential energy. All right, so we have the kinetic energy, we have the potential energy, and hence we should be able to write down the Lagrange function. Which looks like this. So again, this Lagrange function describes the kinetic energy and the potential energy of the system as we have perturbed it a small distance eta I, and eta j in this double sum from equilibrium. Well, from this we can write down the equations of motion, but again, before doing so, we should always consider symmetries and corresponding conservation laws. So what do you think? Any thoughts? Well, I guess nothing obvious comes to mind because unfortunately we don't have any cyclic coordinates here. So for now it seems we're stuck with this, but at least we know that energy should be conserved because we have no explicit time dependence. So the equations of motion look like this. And let's consider these equations of motions for one particular value of I. So we solve them for one generalized coordinate. So I write the Lagrangian in terms of the indices L and J, since we want to now obtain the equation of motion for coordinate I. So keep in mind that this is a double sum. And if you perform this derivation, you would find this. So you get two terms from deriving each of them. And here you only get a contribution when I equals L. And similarly, when you derive this term, you only get a contribution when I equals J. So this becomes the following, and here it's convenient to make use of the symmetry of the kinetic energy matrix. So we expect that interchanging these indices in the kinetic energy, well, since these are scalars, they just commute. So this mass coefficient should be the same if you exchange the coordinates, indices. That wasn't a pretty L. So we make use of the symmetry in this expression here. and find this. So this is the first term, which we should put into here for the Lagrange equation. And if we perform a similar calculation for the second term, we get
Excuse me?
Yeah.
If the coefficients Ti can be dependent on the generalized coordinates,
Mm.
would these also make contributions in the time derivative?
Absolutely. But we assumed here that we only include this constant contribution to lowest order to make both the kinetic and the potential energy second order. So you're right, in general, you would get a contribution from Tij as well. And the second term becomes like this. So our equation of motion for the generalized coordinate qi looks like this. And we'll have a few more things to say about this after the break.